Hello, my physics and universe students. This video is for those people who maybe missed a day or two on the Pendulum lab and you need some help with it. First part of it you can see I've already got done because we did this as a class. Basically, you have a pendulum. The research question I'm giving you guys is how long will one complete swing take when we raise it to 60 degrees? And different people got different answers, so whatever you do, don't copy my answers. I will be looking to see that people are copying my answers. But my wild guess was, I don't know, 1.5 seconds. All right. This part we did do, everybody can copy this one. And we came up as a research question. How does increasing the angle, and that should say increasing, or how does the increase, that's right. How does the increase in angle affect the time it takes the pendulum to complete one full swing? The increase in angle being the independent variable, the thing that you're changing. The one full swing is the dependent variable, the thing that we're measuring, the thing that we're looking for. So from there, we have to form a hypothesis. So this can be phrased in an if, then, because. And it doesn't have to be right. This important thing to say is that this does not have to be correct. It just needs to be formulated with if, then, and because. If we do this thing, then I think this is what's going to happen because give me a reason. For example, and once again, just because I'm doing this doesn't mean that this is the correct answer. This is just an educated guess that one of my students gave me. If we increase the angle of the pendulum, the angle of the pendulum's increase, then it will take more time to complete one swing because if you look at it, the pendulum's got to go a further distance to complete that one swing. Perfectly reasonable hypothesis. From there, we went to Desmos and we put up a graph that kind of shows like the number, the angles across the bottom and the time it takes to swing going across the y-axis. And this is my my guess based on what we just said would be a line that says as I increase the angle, it'll take more time to swing. All right. We scroll down. This next part was right here. It's just making sure everybody's on the same page. You're going to have one person in the group say ready, set, go. And then they're going to let go of the pendulum and the timer is going to hit start. And then you got to say the word stop after one full swing has completed. It tells you got to do three trials. Some of the controls are things that have to stay the same every time. This is why if you started one day, you'd have to restart it a completely different day because things like the length of string can't change. The weight can't change. The timer, the person that's doing the timer and the person who's doing the swing, they can't change. And a whole bunch of the ring stands can't change. I mean, the temperature in the room is not really supposed to be able to change. So there's a whole bunch of controls that have to be. The only thing that should be changing is the angle and the time it takes to swing. The qualitative data, now this answer is going to vary for different people. What are things that could have thrown off your data? Something that might have not been working on your pendulums. I know my earlier periods, there was a problem with the whole thing wobbling. I think we kind of figured that out a little later on. Down here, there's just a parenthesis right here, but the dependent variable, remember, is the time to complete one swing. So that dependent variable we time, and we're measuring it in seconds. So you want to make sure you put seconds there. Now, I gathered some data here from one of my students, and this is what they had got. And to figure out the average, remember the average is these three numbers added together divided by the number of trials I did. So if I were to figure the average, I would use my calculator right here. I don't really need to use a calculator, but I will anyhow. 1.3, 1.6, and 1.0. So can I make this smaller? I'm just going to move this to being a standard calculator to make this hopefully a little smaller. There we go. So 1.3 plus 1.6 plus 1. Oops. I messed up. 1.3 plus 1.6 plus 1 equals, and that comes to 3.9. Now, if you put 3.9 in average, that's not your average. You got to take 3.9, divide that by 3, and that comes to 3. Oop, that is not what that comes to. That is the wrong answer. Well, let's go back and see, what did I press wrong? 1.3 plus 1.6 plus 1.0 equals, and I'm going to divide that by 3. Okay, comes to 1.3. There we go. That makes more sense. 1.3. All right. We're going to do the same things for the next ones. As soon as I figure out what I do with my calculator. 1.1 plus 1.5 plus 1.2 equals that, and I'm going to divide that by 3, and I'm going to get, what am I doing wrong there? Go back one. 3.8 divided by 3 comes to 1.26. Now, I ain't got to leave this in to the nearest tenth. So if that says 1.2, any number greater than 5 will go up. Any number less than 5, we're going to go down. So 5 and greater will get rounded up. 5 or lower than 5 will be rounded down. So in this case, it's a 6. So I'm going to round this to 1.3 as well. 1.3. All right, bring my calculator back. 1.2 plus 1.4 plus 1.1 equals, and I'm going to divide 3.7 divided by 3, and it's going to come to 1.2. In this case, 1.23. We're going to round down to 1.2. The next trial came to 1.2 plus 1.3 plus 1.3 equals, and we're going to divide that by 3, and that comes to 1.26, so we're going to round that up to 1.3. All right, and then lastly, (1.2) plus 1.3 plus 1.3 equals 3.8, and divide that by 3 and get 1.26. We're going to round that up to 1.3. All right, so I'm starting to see a pattern emerge that they're all about 1.2, 1.3. All right, so for the next part, you're going to put the range. We look at the highest number, which would be 1.6, and the lowest number will be 1.0. So that's going to be 0.6. So your largest number minus your smallest number is going to be your range. In this case, 1.5 is the largest number, 1.1 is the smallest number. That's going to be 0.4. The next one would be 1.4 would be your largest, 1.1 would be the smallest, so 0.2. 1.3 is the largest. Okay, so this one's going to be 0.1. 1.3 is the largest, 1.2 is the smallest, so 0.1. And then for the uncertainty, we just put in the average, 1.3, and then we say plus slash minus, whoops, that's not a plus, plus slash minus, and then we take half of the range. Half of 0.6 would be 0.3. All right. In this case, 1.3, that's our average, plus or minus. Half of 0.4 would be 0.2. A little bit more accurate on that one. This one would be 1.2 is the average, plus or minus 0.1. Half of 0.2 would be 0.1. And then this one's going to be 1.3 plus or minus half of 0.1 is going to be 0.05. And looks like it's the same one for the next one, so I'm going to cheat and hit copy and then go down to the next one and hit paste. All right. Now what I want to do is I want to get these numbers into Desmos. So I'm going to open up this Desmos program. And right here, this is the angle of the swing. So this is your x-axis, this is your y-axis. So this is your x-axis, the angle of the swing. So the angles, I remember off the top of my head, we did 10, degrees, 20 degrees, 30 degrees, 40 degrees, and 50 degrees. All right. And this is the actual swing. So for 10 degrees, it was 1.3. That was the average. So I would type in 1.3. The next one was 1.3. 1.3. 30 degrees was 1.2. 1.2. All right. And 40 and 50 degrees looks like they were both 1.3. So we can type in 1.3 and 1.3. All right, and I'm starting to see a pattern here. And what I need to do is I need to put a line in there. Now, Desmos has a way of doing this. See where this says A equals 0? I'm going to move that until this line, this purple line, is inside all of the boxes and touching or near touching most of the dots. So that's the purple line. That's the line I want to keep. I'm going to exit out of the green, the blue, and the red. Now, if I accidentally hit the purple and it disappears, that's fine. I can just hit go back and I can get it back. All right. So the boxes is your uncertainty. So that tells you how much it'd be off. So you're all within the uncertainty on this box. Okay. So that would be, 1.3 plus or minus that 0.1. Okay. So this is the line that we're going to use. If we look, this purple line right here, it says that y equals a. What that means, that's your mathematical formula. That means that a is 1.2. Let's see, about 1.2 would be about right here. It doesn't matter what x is. X could be 20. It's going to be 1.2. X could be 40. It's going to be 1.2. That we're pretty much all on this line where it's always going to be 1.2. So y is always going to be 1.2. So keep that in mind. This is your mathematical formula, the mathematical expression of what your answer is going to be. This is called a horizontal linear line. That's going to come up in a moment too. But for now, I've got to get this image into this box. So what you need to do is go back to this image, hit the snipping tool. I already got the snipping tool in my toolbox here. I'm going to hit new. And I'm going to make sure I want the mathematical expression to be there. I want that A right here to be shown. I want to make sure it have my axis and of course all my data. So I'm going to hit new and I'm going to hold down on my left mouse button, drag, and there we go. Now I've got a copy of the image. I'm going to right click on that copy and hit copy. Minimize that. Go back to my lab and now I can hit paste. And there we go. There's my image pasted a little bit too large, but there we go. Inside the box. All right, so it says, what's the mathematical model? Well, for my graph, it was y equals a. Y equals a. All right. All right, so this begins the conclusion. Now, typically conclusions are in paragraph form, but since we're just starting to learn, we are just going to kind of fill out a little form, and later we would turn this into paragraph form, but using the same structure. After investigating this behavior, what did we find out? Well, we found out that there is a relationship between the angle of a pendulum and the time it takes to complete one swing. All right, I conclude, in other words, what happened? Okay, well, what did I conclude? I conclude, first of all, my hypothesis was incorrect. Because it looks like, by looking at the model, that the numbers don't increase, they stay the same. My hypothesis is incorrect because the time it takes to swing complete one full swing is about the same for all angles. Okay, so what's the relationship? The relationship between the IV, the independent variable, which was, instead of writing independent variable, you would write the angle, and the dependent variable, the time it takes to complete one full swing, okay? The evidence is that the best fit line is what kind of line? And this is the one I told you earlier in the video. It's called a horizontal linear line. Shows that the time is always the same value. In this case, this can be represented as the y equals a. But in my case, if we look at this, it says y equals a, but a equals 1.2. So I would say that y equals, and you can resize this to make sure it doesn't look so weird, y equals 1.5 seconds. It was always, oops, 1.2 seconds. Okay, now everybody's going to have a different answer there, but that always works. Y always equals 1.2 seconds. So using this model, I can predict, all right, well, if we did 10 and it was 1.2 seconds, if we did 20, 1.2 seconds, so they're all about 1.2, 1.3, somewhere in there seconds. We didn't do 60. But what's 60 going to be? Well, your x-axis is 60. That means we go up to the y-axis, and it's going to be, well, 1.2 seconds. So I can predict the time it takes is the pendulum swing is going to be about 1.2 seconds. All right, research extension question. What would happen if you went to 110 degrees? Now, I can't answer that question. I want you to think what would happen. Remember, 90 degrees was the highest our pendulums went up to. So you'd have to go 20 degrees higher. Would we get the same thing? And don't just put yes or no. Make sure you explain what would happen, why it would happen that way. And then that's it. At that point, you would just submit this lab, and we are good to go. Thank you guys for watching. I hope you have a fantastic day.